My name is Daniel DeSantis, and my call sign is KC3FKR. We're going to be talking about a little bit of the inside technology of SDRs, or software-defined radios. So, I know a lot of us are very familiar with the RTL-SDR dongles. I'm sure many of you have them, maybe use them for AM reception, as they can make pretty good AM receivers. You can make them do synchronous AM detection, all sorts of good stuff. And maybe some of you have flex radios, and those are another type of SDR which operates on the same principles as the RTL-SDR, however slightly different in implementation. So a lot of us might think of complicated black boxes with not a lot of rhyme or reason to what they're doing inside when you think of an SDR. And the goal of this presentation is to clear some of that up. So in order to do that, we're going to talk about a couple of things listed here. We're going to review some traditional analog techniques for radio. And we're going to talk a little bit about data conversion. We're going to review some different types of SDR topologies, which include direct sampling, single conversion, and IQ sampling. And then we can dive a little bit into how you actually do digital demodulation in the very end. So going back in time, there are three types of analog receivers that come to mind when I think of early tube type analog radio systems. Firstly, the tuned radio frequency receiver. Second, around the same time period as the regenerative receiver. And third, a little bit later, is the super heterodyne receiver. The tuned radio frequency receiver was a very simple type of receiver which only used filtering and amplification to amplify a desired AM station many times. So you'd have your signal come in through the antenna, a bandpass filter would pre-select or eventually select exactly the AM station which you desired to listen to, and the resulting signal would be amplified and fed to another stage of filtering and amplification. The more stages that you used in this chain would correspond to higher gain and higher selectivity. So a very sensitive and selective receiver would often have many stages, much like this design here. The resulting signal from the amplification and the filtering would be passed to a envelope detector like this guy here, which was typically implemented with a vacuum diode and some sort of peak detect circuit to demodulate the envelope off the carrier. Moving on, a regenerative receiver was invented, which accomplished a similar feat using feedback. Feedback was, in this case, positive feedback, and it operated in this loop here, where the incoming RF signal was filtered with this tank circuit, amplified by an amplifier, and fed back to the tank circuit with a tickler coil. And the tickler coil would be adjusted in how well it coupled to the main tank circuit in order to increase or reduce the gain of the regenerative stage. This would often be the regeneration control. And similarly enough, if you were actually able to get near the point of oscillation, you could get this RF amplifier to oscillate, and it would also be able to demodulate sideband signals and CW. A few years later, the super heterodyne receiver was introduced, and instead of moving your receiver's filters to the frequency of interest, to the station of interest, the incoming RF signal was shifted to an IF frequency, an intermediate frequency. And what does that mean? Well, this topology has fixed filters and fixed IF amplifiers. They never are tuned. What is done, instead of moving the entire radio's passband to the desired frequency is the desired frequency is shifted to match the radio's passband using a mixer and local oscillator. And what this achieves is frequency conversion, where you could translate a frequency, say at the broadcast band, maybe at 1 megahertz, down to an IF frequency of 455 kilohertz, which was very common in broadcast receivers and still is today. So in software-defined radio, we have to figure out a way to accomplish the same task, but entirely digitally. And this may seem trivial at first glance, but really there's a lot involved with getting your radio signal into the computer and out of the computer. And that's kind of what these boxes are here and here. The first box converts your analog signal, and maybe this is your received signal, your IF, or maybe at RF. It enters this mystery box. It comes out as a digital signal, which is then interpreted by a digital processor. And in some cases, this might be your computer. This might be a chip inside of your radio. Say in an ICOM IC7300, there's a special chip in there which does the processing. Or maybe this is even simpler and it's some discrete logic. Depends on how advanced you want to get. But this digital processor, for the entirety of this presentation, I'm going to refer to as a DSP, or digital signal processor. And this is essentially your signals computer. So it enters digitally and leaves digitally after being demodulated. The demodulation is occurring entirely within this digital signal processor, the DSP. The resulting output is still digital because it's processed by a computer and must be then converted back to an analog signal. So what are these mystery boxes other than an analog to digital converter, an ADC, or a digital to analog converter, a DAC? So the entirety of the signal chain going in and out starts analog, it becomes digital by being sampled with an analog to digital converter, and once it's been demodulated, that digital demodulated signal is then converted back to the analog signal which you hear through your loudspeaker. So we're going to take a little bit of an opportunity to talk about data conversion and how it relates to SDR. Some things that come to mind are aliasing, which you may have seen using an RTL-SDR dongle, and even pitfalls due to low resolution and high noise. So I'm going to talk a little bit about analog to digital converters, and they operate in such a way that they convert a incoming analog signal, a voltage, a continuous voltage, to a string of bits, and the length of that string of the bits is determined by its resolution. And when you have a certain number of bits, say 10 bits, that will correspond to 1024 discrete quantization levels. And quantization really just means rounding, for lack of a better word right now. If I have a incoming signal that looks like that, and I have so many levels, I can split that into maybe like this. The rounding is going to occur and look maybe something like this and turn into a stair step. And if you have more and more levels, you can more accurately represent that incoming waveform. So generally, you will find ADCs with resolutions like 8 bits, maybe 10 bits, 12, even 14, 16, all the way up to 24 and greater. I haven't often seen weird resolutions like 11 or 13. Those aren't very common. But anyway, I digress. The types of these ADCs are categorized by comparator-based or flash ADCs. These convert your voltage signal almost immediately after sampling. There are successive approximation register ADCs, or SAR ADCs, and these essentially do a algorithm where they have a counter count in a very clever way to eventually have a comparator compare an output DAC to the incoming voltage, and when they're equal, it says, oh, I found the right voltage, so this must be the right level. So that's a similar way to do it. It takes a little bit more time. Another thing that takes a little bit more time is something called sigma delta modulators, or sigma delta ADCs, and these work by converting a frequency, or converting a voltage to a frequency and measuring that frequency. Something that might be interesting to some of you is a very old type of ADC which was built using a cathode ray tube of sorts and some deflectors which would scan a linear beam of electrons across the shadow mask right here. And this shadow mask was configured such that if you place detectors directly behind each of these grids, as the beam scans up or down, the detectors would detect a high presence of electrons or low presence of electrons. And since this mask is, if you can look at it, and you might see it or you might not, this mask is counting in binary. So as the mask increased its height on this collector plate, the resulting output from this tube would be a digital number depending on the voltage across the deflectors. And that was built at Bell Labs back in 1948. Kind of an interesting type of ADC. And I might note this is a flash ADC because the result is almost immediately available. So delving a little bit more into flash ADCs, they can be configured with comparators and a string of potentials which represent your levels. Maybe this is your high level, here's 2 intermediate levels, and your lowest level. So these correspond to the only 4 levels that this data converter can discern from your input signal, which comes in down here. At a certain instance, it is held using a sample and hold circuit, and that allows the comparator's time to generate their outputs depending on where that voltage is in this slew of potentials. Now, if you want n bits, if I want 8 bits of output resolution, I need to be able to discern 256 levels. This diagram I have drawn here is only a 2-bit ADC. So if I want to go to 8 bits, I need 256 comparators and 256 precisely adjusted potentials to act as their reference. Now, you can see how that might become cumbersome on a discrete design, and there are ways of reducing the number of comparators used by using folding techniques and whatnot. But getting high resolution from a flash ADC requires very large scale integration on, say, an ASIC or a purpose-built integrated circuit like you would buy off the shelf at DigiKey. So a lot of these are not built discretely anymore. They used to be, but nowadays you can get pretty high resolution flash ADCs at moderate speeds. At high speeds, you can get low resolution flash ADCs because the result is almost immediately computed. So you have a limited number of comparators and a really high speed. It allows you to achieve maybe gigasample per second rates, and the trade-off there is you give up some resolution. To get both of those things, you're obviously going to spend a lot of money, and we've already talked about the scanning electrons. Sigma delta modulator ADCs, or most oftenly just called sigma delta ADCs, take an input voltage, they convert it to a pulse train, a frequency in this block here. This pulse train is then counted with a counter over some predefined interval in time. So this is a time reference maybe this is 1 second. And if the counter counts 300 times, well, that means that the frequency was 300 hertz, and that output is here, 300. If I increase my voltage, my Vn goes up, then the counter will see a higher frequency because the output frequency of this circuit here is proportional to Vn. So the counter will ultimately count maybe, let's say, 12,000 hertz. And that will be the result of the buffer output. So these systems can achieve very high resolution simply by increasing the amount of time over which you're summing. And if you work out some of the math, the number of bits that you're able to achieve with this, the resolution in bits you're able to achieve with this type of converter is proportional to log base 2 of the maximum integrator frequency. So if you can make this clock run really fast, maybe at several hundred megahertz, if you can make that really fast and you can make the sample rate very low, maybe only 100 samples per second, you can achieve extremely high resolution simply due to the fact that you have more granular control over this frequency and granular control over how well you measure the frequency. It's just like any frequency counter. The longer your gate is, the more resolution in hertz you get when you get the result of the frequency counter. Something we run into when we sample a signal is called aliasing, and it's a product of having a finite sample rate. So we can't sample at an infinite frequency, otherwise somebody would have a Nobel Prize by now for that. The resulting samples from the ADC occur periodically at the sample rate. In this case, the sample rate is 1 kilohertz because we get a sample every 1 milliseconds. And sorry, this is kind of not easy to see the way I have it, but this is times 10 to the minus 3. So each one of these divisions is 1 millisecond. So we get a sample every millisecond that corresponds to a 1000 hertz sample rate. And if I'm sampling a 400 hertz tone, I'm going to get sample points here, here. These black diamonds are all my sample points. Now, if I increase the frequency of that signal to 500 hertz, which is coincidentally 1/2 of the sample rate, the resulting samples form this periodic 1, -1, 1, and so on. What happens when we go to a slightly higher frequency, in this case 600 hertz, is, well, the ADC takes the 600 hertz signal in. However, it's only able to sample every millisecond. So it's missing part of the waveform in this region here. The resulting samples, if you compare them to the first plot, look remarkably similar. And that's because they are in terms of the sampled data. The data set from a sampled 600 hertz signal and a sampled 400 hertz signal are identical when sampling at 1 kilohertz. And this is because the alias of the 400 hertz signal is at 600 hertz as well, or vice versa, depending on which way, depending on your Nyquist zone of interest. But this is what's commonly known as the Nyquist rate, or the Nyquist criterion for sampling. The sample rate must be greater than, and usually much greater than, twice the bandwidth of the signal you're trying to sample into your front end, your digital front end. And that also means that the maximum frequency you're able to accurately sample is equal to half the sample rate. And that's why we were able to see a unique solution for 500 hertz, but not for 600 hertz. We exceeded that F sample over 2 limit. So what does this mean for ham radio and for radio receivers? Well, if I want to digitize an IF signal at 10.7 megahertz directly, well, then I better have a ADC, or an ADC with a sample rate much greater than 21.4 megahertz. Otherwise, I will run into this aliasing issue and frequencies will fold over on one another, And that's what you're about to see here. In this case, I sort of set up a simulation which might be something you come across in an IF conversion scenario. I have two cosines, two sinusoids, one at 450 Hertz, one at 650 Hertz. And they're both added together, and for realism, a little bit of white noise is added as well. All this is added together and then sampled with an ADC, and the resulting data set from the sampling is then passed to a fast Fourier transform, or FFT, which gives us this plot here. You can see that we get our expected signal at 450 Hertz here, as we had a cosine at 450 Hertz entering the ADC. However, our signal at 650 Hertz, which would be out here somewhere, is folded over and pops up here at 350 Hertz. And that's kind of confusing at first, but what's happening is precisely what we saw in the previous plot. The 650 Hertz signal looks exactly like a 450 Hertz signal when sampled at 1 kilohertz. And that's because we did not obey Nyquist criterion for sampling. Now, we can get around this by placing a low-pass filter in the signal chain to the ADC. What this does is filter out any signals which exceed 500 Hertz in this case. So this would have a cutoff of 500 Hertz. And that cutoff, in this case, would have to be a brick wall cutoff, because anything above 500 Hertz, you're getting fold over, you're getting aliasing. So typically what's done is I will turn my sample rate up to, say, 10 kilohertz, and that will allow me to have a more gradual frequency response with my cutoff at 500 Hertz, because I won't see aliasing until 5 kilohertz. So that gives me a full decade of rejection. So that's 20 dB if it's a first order filter. So this is something you might see pretty often when buying an oscilloscope, especially a digital oscilloscope, a storage scope. You often hear the terms that you want to oversample by a factor of 10 from your bandwidth. If you have a 100 meg scope, you better have a gigasample per second scope. And that's where this comes from. It's simply because you can't reliably make a brick wall filter with good enough characteristics for most applications and sample at exactly the Nyquist rate. Oftentimes you have to fudge it a little bit and multiply that by 10. Now, another pitfall from sampling is inherent to the rounding error which occurs when you quantize an analog continuous voltage to discrete steps. And this quantization error is simply the difference between the blue waveform, which is our analog input waveform, and the red waveform, which is our digitally sampled waveform. The difference between our analog waveform and the digitally represented one, the discrete time set sample, is this blue plot, this quantization error plot. Now, if you've ever listened to a low quality CD, you've often maybe heard this quantization error signal as a weird sibilance or very strange artifacting in quiet parts of the song. And that's simply due to the fact that your ADC that originally sampled this data to put it on the disk may not have had enough resolution to faithfully reproduce the signal with low quantization noise. And this quantization noise is relative to your quantized signal at full scale, such that your signal to quantization noise ratio, or SQNR, if you do a little bit of math and you make some assumptions about your input waveform, your SQNR is proportional to your resolution. This 2 to the n bits is the number of levels, and 20 log is converting that to dB. So if you do a little bit of math, you find out that your signal to quantization noise ratio is pretty much exactly 6.02 times the number of bits your ADC can sample. So how does this play in a receiver in a software-defined radio? Well, let's take a couple of scenarios. This first scenario of 8 bits, this is like your RTL-SDR dongle. Your RTL-SDR dongle actually has 2 ADCs running at 2 megasamples per second and 8 bits of resolution. More realistically, since they're cheap ADCs, they have a lower effective number of bits, but we'll assume they're 8 bits for now. If you plug that into our equation, we find out that we have a signal to quantization noise ratio of 48.16 dB. And that's not a lot. If you think about a high-end receiver might have a signal to noise ratio limit of 100 dB if you do the analog design correctly. So by using a low resolution ADC, you're throwing away SNR by injecting this quantization noise as a result of imperfect sampling. We can improve that signal noise ratio dramatically by increasing the resolution. Now I went from 8 bits to 24 bits. This would be similar to using a soft rock SDR system. Those use your computer sound card, which can be configured to operate often at 192 kilosamples per second and a resolution of 24 bits if you have a decent sound card. And that affords you a significantly larger signal to quantization noise ratio of 144 dB. If you can design your RF front end correctly, you could use this system to almost measure the thermal noise floor of your antenna, which is rather funny. The noise floor and dynamic range, if you're not careful, can be absolutely driven by the low resolution of your ADC. If you don't have enough bits, you're going to have terrible noise floor, and those weak signals, those weak CW signals or weak AM signals, you just won't be able to receive them. And it's not because you have a poor antenna, it's not because you have poor RF gain, it's simply due to the dynamic range limitations of the ADC due to its low resolution. So we've seen a bunch of parameters of these ADCs, and first of all, we talked about sample rate and bandwidth, and these are governed by the Nyquist criterion. And we also saw the trade-offs between resolution and noise performance. You want high resolution to get high noise or high signal noise ratio. But unfortunately, if you want high resolution, it's very expensive to get high sample rate. So if you want to get both of those, high sample rate and high resolution, then you're going to pay a lot of money. And this is kind of where the flex radios fall in that category, which is why they cost so much. Additionally, once you've actually converted your signal to digital, the computer handles the demodulation, but actually getting your signal from the antenna into the ADC is somewhat arbitrary and can be done in many ways. 3 of them that I'm going to talk about are direct sampling, which is this one, signal conversion, which is like a super heterodyne system, and quadrature sampling, which actually uses 2 converters. Direct sampling receivers you might be familiar with immediately are the ICOM IC7300. The ICOM IC7300 simply has an RF antenna, some selectable bandpass filters, and some very good RF amplifiers which directly feed a very high-speed ADC, which then gets digitally down-converted and demodulated by its internal processor. And there's some really good aspects of this. The RF design becomes very simple. You don't have many boards. IF alignment's not necessary. All of the difficulty in designing a very good receiver using transistors and discrete components drops away in favor of having to deal with designing a very good digital system to do the demodulation. You get extremely good low harmonic and third order distortion characteristics simply due to the fact that you're not using mixers or nonlinear components in your RF signal path. The RF signal comes in, it's amplified in a very linear manner and digitally demodulated without introducing any nasty nonlinearities. For low carrier frequencies such as the HF bands, these topologies are very attractive simply because the maximum frequency that these receive, especially the 7300, this only receives up to 6 meters or 50 megahertz. This allows a relatively lower speed ADC to be used. And in the ICOM IC7300, if you look up on some forums, some gurus have found that the chip that they're using in there is a 130 megasample per second 2-channel ADC. Or I'm sorry, it's just a single channel ADC. The chip they're using in there is a high-speed 130 megasample per second ADC, I believe operating at 12 or 14 bits of resolution, and that allows you to safely digitize the entire HF band all the way up to 6 meters without violating Nyquist criterion. Where this topology begins to suffer is if you need to sample a very high frequency signal, say something at 70 centimeters, 440 megahertz. You have to think about oversampling. You might be talking about a 1 gigasample or 2 gigasample per second ADC, and those can get very expensive at the resolution required for the very weak signals up on those bands. So again, you're kind of always limited to flash ADCs, because we talked about flash ADCs are the fastest to achieve a decent sample rate, which corresponds to a low resolution and a higher digital noise floor, and it just kind of falls apart at very high frequencies unless you're willing to pay several tens of thousands of dollars for Xilinx's latest integrated RF systems on chip. So those are some of the drawbacks for this topology. Also notably, Flex Radio, they're also direct sample in case you were curious. So if you take a look at what we talked about before, the tuned radio frequency receiver essentially had an antenna with some filtering and amplification, which would directly go to an envelope detector. And this envelope detector simply did AM demodulation, while direct sampling SDR takes the front end of a tuned radio frequency system and attaches its output to a DSP, an ADC feeding the digital signal processor and the DAC to recreate the audio signal at the end. And the advantage to this is you're no longer limited to amplitude modulation, simply due to the fact that this DSP can pretty much demodulate any mode imaginable, and we'll talk about that later as well. Moving forward, single conversion SDRs operate very much like a super heterodyne receiver. You can see we have a super heterodyne front end feeding our DSP signal, and this solves the problem of needing a very high speed ADC. If you only need a small instantaneous bandwidth, you can get away with a low speed ADC with high resolution, and you simply shift your high frequency signal coming in at your antenna down to a more manageable near DC IF frequency, which can be then sampled and digitized with a lower speed, high resolution ADC. So again, this is great and all. However, now we've introduced some nonlinear components, this mixer, and that mixer can add third order distortion, intermodulation, and all sorts of nasty things which you might not want when designing a receiver. So your RF design gets a little more complicated in favor of your digital design getting cheaper. So the soft rock SDRs use this topology exactly. They convert whatever band you bought the receiver for down to a near DCIF. It's actually a DCIF, and that is sampled using your computer sound card ADCs. again, this is also employed in the RTL-SDR. However, there's a slight modification to it, which we'll talk about soon. A very large disadvantage to this design is imaging, whereas if you have an LO, say, tuned to downconvert a signal at 1 megahertz in the broadcast band, if there so happens to be another signal at 500 kilohertz, the two signals, when mixed and amplified in your signal chain, will overlap in the same spectral domain that your ADC is sampling. And there's no way to discern these from each other without using complicated LO dithering approaches. So there must be a better solution entirely, even for this. This seems to have solved a lot of our issues, but we're missing one crucial step. And this is where things might get a little bit interesting for some of you. We get into what's called quadrature sampling, or in-phase quadrature IQ sampling. This is almost identical to what you just saw, and all we really did was take the RF front end from a super heterodyne receiver, take the IF, and then at IF frequency we generate a cosine and a sine wave flipped 180 degrees out of phase to then mix with the identical IF frequency or IF signal from our receiver. This produces two signals, one in phase and one quadrature phase signal, which is then amplified and detected with two separate ADCs to generate a digital I signal and a digital Q signal. Both of these signals are sampling essentially the same IF frequency, the same IF signal from our front end. However, one is representing the in-phase component, the real component, if you will, of the IF signal, and one is sampling the imaginary component of the IF signal. This allows us to solve, and what will become apparent a little bit, the foldover or the imaging problem from the single conversion receiver by being able to resolve negative frequencies. And that might stand out at you like, what the heck is a negative frequency? It will become apparent when we talk a little bit about the characteristics of I and Q in a little bit. You effectively double your bandwidth of reception by using two ADCs, because now you've effectively sampled the same signal with a phase shift at the same rate on two separate ADCs, so it's effectively like having twice the sample rate. And you also solve the image rejection problem by, again, having negative frequency resolution capability. Again, now you've added more mixers, so you're going to have more nonlinearities and so on. You need RF alignment to make sure that this thing will operate. You need to align this IF stage here. And just like any good super heterodyne receiver, you need to select these mixers carefully. The Hack RF, the Blade RF, most high-end SDRs, they all use this topology, and also the RTL-SDR dongles. So what we've made with our I and Q signal is what's called a phasor in electronics, and some of you might not be familiar with what a phasor is. It's not this type of phasor, spelled with ERS. This is not a Star Trek episode, but spelled with ORS. A phasor is really simply a complex number defined by Euler's relation, which, if you are an engineer among us, you might remember as some amplitude times e to the j phi, or your phase. And all it really represents is an amplitude or magnitude and a phase. So a cosine wave can have an amplitude, and a sine wave can also have a phase shift. This could be out of phase slightly, and that phase is accumulated in this phi term here. So these are useful for analyzing the response of systems in the Fourier domain. It's essentially everything to describe a sine function with just two numbers, an amplitude and a phase, and that can be at any frequency in the frequency domain. So some of you might be familiar with Bode plots, and Bode plots are simply a plot of a phasor decomposed into its relative terms in what's called polar notation, magnitude and phase. So the magnitude of this plot would be the A in dB, and the phase is simply this red plot, and the red plot is corresponding to the phi term in this ae to the j phi function here. Now, when we generate an I and Q signal, we've essentially taken our IF, our x of t function, we've multiplied it by a cosine and minus sign, which if you back up will look very similar to multiplying by this phasor term. And what we've made is what's called the bandpass equivalent signal or equivalent phasor, in which the I signal here represents the real component and the Q represents the imaginary component. You can imagine if I had a cosine and a sine representing my I and Q, that means I just have a tone in my IF passband. That will just correspond to this phasor rotating counterclockwise. Now, where it gets interesting is when I introduce signals above and below the IF. So if I have a positive frequency offset from the IF center, I have a counterclockwise rotation of this phasor. My I and Q are both positive sine and cosine. When I have a negative frequency offset from the IF center, what occurs is a phase shift or a flip of the Q term. So the Q signal will flip its phase 180 degrees, and the digital signal processor can then interpret that as being below the IF center. What this allows you to do is completely distinguish between our two frequencies which originally overlapped. And this is great because not only does it give us distinguishability of signals above and below the IF, but it also expanded our bandwidth by a factor of 2 as a side effect. And again, in the complex plane, we have our I and Q signal represented as the x and y component of this vector, and the polar representation, the amplitude of this vector, is simply the amplitude of the sine wave, and the phase, the phi term here, is the phase of that waveform. So, digging back into this, now that we've fixed all of the problems, we can resolve negative frequencies, we can resolve rejection issues, we've doubled our bandwidth, which is great. Now we can get into a little bit more about why I and Q sampling is great from a digital signal processing perspective. Any arbitrary modulation can be demodulated with the I and Q data. I and Q are a complex representation of your IF signal, and pretty much all DSP that you can just download to do demodulation for AM, FM, what have you, accepts a complex input waveform which requires both I, the in-phase and quadrature component of your IF signal. So that's where this gets interesting. For amplitude demodulation, you can very easily get the envelope or the amplitude of your signal by just looking at the magnitude of your IF passband equivalent signal. And if we go back here and take a look, the magnitude is really the distance from the origin to the point on this circle where it rides on this constant radius path. And the astute of you might realize that, well, this distance is the radius, and the radius of this circle, since it's outlined by this I and Q coordinate, would just be the distance formula from the origin to that point on the graph. And that is exactly what it is. It simply becomes the square root of the I squared term and the Q squared term. And as your message varies the amplitude, the amplitude of your carrier in your IF passband, the resulting magnitude, or the result of this equation, will vary up and down. You can see that on this green plot, which corresponds to a couple different circle radii there. For single sideband, a very clever technique called the Hilbert transformer, or the phasing method, can be used to demodulate sideband. Some of you might be familiar with phasing receivers, phasing transmitters. They simply took your amplitude modulated system, and instead of directly modulating a audio signal onto it, the audio signal was first phase shifted by plus or minus 45 degrees and summed in the modulation stage, such that the lower sideband and the carrier are rejected. This is the exact same technique, although in reverse, where you take your I and Q passband signals and phase shift, in this case the Q arm, by 90 degrees, adding or subtracting them from each other, and by them I mean the I and Q component when phase shifted, will yield either upper or lower sideband demodulation. And here's a good sort of mathematical way of looking at it. If I had a frequency above the LO, a cosine wave, and a sine wave as my Q, when I phase shift that by minus 90 degrees, I end up with a cosine wave but inverted by minus 1. If I add these two signals together, that will correspond to getting nothing on my output. I will get 0. They will perfectly cancel out. I will only get a useful signal if I subtract them. So when I do a subtraction of I and Q, I'm demodulating the upper sideband. If I'm adding the two signals, I will demodulate the lower sideband with very good rejection, depending on the length of this Hilbert transformer in taps. It gets a little bit more advanced. So again, here is a modulation scheme for a Heathkit SP10 adapter, and you can see it's forming the same type of system here. You have an RF input, it splits these by 90 degrees. This forms your I and Q modulator signals. You have an SSB signal, which will be generated by a 90-degree phase shift network, just like we described earlier, and fed to two modulators. And the resulting signal is either added or subtracted by this tube, and then amplified and sent to the output for your linear. So this is the original way to do it. There is several other methods, including a filtering method, and there's also another one which employs a similar approach, although it uses filters and 2 stages of modulation. Rather interesting. Finally, for FM demodulation, we can take advantage of knowing that I and Q represent a phasor of our signal. And angle modulation, which is a brother to FM modulation, the phase of a frequency modulated signal in our phasor form can be figured out with trig using tan inverse of Q over I, because that's because we have this vector here, and this side is the Q, and this side is the I. You might remember from trigonometry way back when that the tan of our angle is equal to the opposite over the adjacent. In this case, that's Q over I. And since we're concerning ourselves with the time rate of change of phase, which is the same thing as frequency in radians per second, we can do a little bit of creative calculus here and define that the frequency of our IF signal as a distance from the center passband can be written as the derivative of this function. And if you do some calculus, you yield this equation, which then can translate into this block diagram. And this is pretty common. You might see this on the internet somewhere. This is a discrete time frequency discriminator. So there really is no limit to what you can do with these software-defined radios. I kind of consider them to be the Arduino of radio, for those of you who are familiar with Arduinos. It can be reprogrammed to do really whatever you want. You can invent a new modulation mode, whatever you want to do. It's all there. You don't have to design hardware. You just have to do a little bit of block diagram design for how you want your signal to be processed, and you're off and running. And a really good way to get started with that is the GNU Radio Companion, which is a graphical user interface designed for helping you design these block diagrams and test your processing algorithms without ever really having to do any math or write any code. And there's plenty of SDR systems these are compatible with. You can use them with your RTL-SDR, HackRFs, sound card, INQ, like a soft rock system can work. Pretty much any plugin you can get for this software. I think you could probably get a Flex Radio to run this way as well. You have access to a really fast DSP system which is optimized in C, and you never have to really write any code unless you want to do your own Python version of it, although not many people do that. This is sort of the Arduino IDE of software-defined radio, and it lets you really play around with anything you want. You can do FFTs, you can do pretty much any list of DSP operators from anything from OFDM demodulation, digital TV demodulation, PSK31, JT65, whatever floats your boat. You can get plugins to do the demodulation for you.